That's pretty funny. I can see me here. And this other one. So I'm recording now. Oh, it shows that, huh? Oh. All right, let's go to Lima. And today is September 5th, which is this day. And we're starting Chapter 4. And so let's look at Chapter 4. See, where would my book be? I got a book around here someplace. Is it like... this one? Must be this one, huh? Yeah. And slides. Do I have slides around? Well, let's go to Chapter 4 and see what it is. Relational operators. And, oh yeah, great. So now we're getting into relational operators. I'd like to do this, and this, and I don't really need this anymore. So, Codd's original algebra, it's the point there. It's very important. This idea of the closure property where you can nest relational expressions. It's like nesting. It's like being able to nest functions. Well, you can nest functions in programming languages. Well, it's important that these operations were such that you could have an expression which resulted in a table or a rel bar, and that can be inside the expression of another, rel bar with another expression. These are some basic, we're going to first learn basic relational operations, and then we're going to learn some more advanced ones. But the first basic ones we're going to learn are restrict, project, and then product. And these are can be illustrated using this diagram here. I want to see what's on the slides. So that would be here, resources, inside here, and we're doing Chapter 4. Is this really part of this? And so it's this describes this is this picture I just had showed you out of the textbook. And what is this here? Okay, so if these aren't obvious to you, restriction means that you somehow using an expression. It's actually a Boolean expression that's applied to every tuple, whether to include it or not, and that's called a restriction because you're restricting the tuples that are in the new rel bar, or you're subtracting out some tuples is another way to look at it. Projection means you're only choosing some of the columns, not all the columns, and that's illustrated this way. Product means you're taking all combinations of the two. So, if you have a complete rel bar X or whatever, a complete rel bar and another complete rel bar, and you just combine each tuple, all combinations of taking a tuple from one and a tuple from the other. Okay, so that's this. So the left rel bar's got 3 tuples in it. The right rel bar's got 2. And so you take all combinations and you just append them together, you know. You just concatenate the tuples together. And you end up with something, you know, with this, which is, you know, all combinations. So there's an A and an X and an A and a Y and a B and an X and a B and a Y and a C and an X and a C and Y. So that's illustrated here. That's product. That's cross product. Okay, and then there's this intersection, which is pretty obvious. And basically, you're taking, it's not quite, I would illustrate it a little differently, but you're taking these tuples that are in both rel bars, the set of tuples that are in both rel bars, obviously. The union is the set of tuples that are in either or both. And difference is you have rel bar A and rel bar B, and all of the tuples that are in common are removed from the first rel bar, from rel bar A. So in this here we have this, the intersection is the set of tuples that the two rel bars have in common, and so this illustrates that they are what's taken out, and the result is the tuples in rel bar A that are not in rel bar B. We have a natural join, and natural join has to have a there has to be one or more columns that are identical, that have the same name and the same, you know, primitive property. They're the same, like in suppliers and the supplier parts. There's a common column, which is SNO, and so those two rel bars can be naturally joined. And basically, what you do is you match up the common column. You match up if a particular value, you know, an attribute of a rel bar, you know, if they're in common, then that pair of tuples is included. If they don't have any matching, if there aren't any matches with the other rel bar, there's not. So to illustrate this, that I'm sure that didn't make too much sense when I just explained it. To illustrate that, we have two rel bars here, and each of the rel bars have 3 tuples. Okay, the first rel bar's got an A1 and a B1, and it's got an A2 and a B1, and it's got an A3 and a B2. The second rel bar's got a B1 and a C1, a B2 and a C2, and a B3 and a C3. So the columns that are the same are column B. This is a funny way of illustrating it, but it's the right column in this first rel bar, and it's the left column in the second rel bar. And so you match them up, and so for all of them where there's a match, that is included in the result. So there's a B1 here, and there's a B1 here. So A1, B1, C1 is going to be over here. Oh, there it is. And then also, okay, so there's a, now if we go down to the second one, there's another B1 here, there's an A2 B1, and a B1 C1. And so that's what we see here, A2 B1 C1. There's a A3 B2, that's this matching here, so there's a A3 B2 B2 C2, so there should be an A3 B2 C2 in here, and there goes A3 B2 C2. There's no tuple over here that with a B3, so so this last tuple here in the second rel bar is not going to get matched with anything. So it doesn't appear at all here. There's no B3 at all in this rel bar. So, and there's no C3 either. So this didn't get matched with anything. The last tuple in the second rel bar didn't get matched with anything. The first tuple in the second rel bar got matched twice. You see this one's here and one's here. The second tuple in the second one got matched once, and that's the last one here, and the third one didn't get matched at all. So anyway, that's natural join. And we do a lot of natural joins. Actually, in Codd's original algebra, there was another operator, which was division, but it's never kind of went anywhere, I guess. But we do have something called image relations, which are kind of cool. And it's one of those things where we just don't really think of image relations a lot when we are when we're writing SQL. It's sort of we learn it here, and we see the usefulness here. But when it actually comes down, 2 years from now, if you're writing SQL code, you're probably not going to think of a solution to a problem where, oh, I could use an image relation there, because it's kind of theoretical, but they're kind of interesting. Relational division didn't solve the problem anyway. Okay, so now we can start using the database for real work. We can issue queries, which are retrieval requests using operators of relational algebra. So just so you know, these operators are read-only and set level. We're dealing with sets. And also note that relations form a closed system under the operators of relational algebra, which means that's where it's because of that you can have relations inside expressions, larger expressions. You can nest, you can nest expressions using parentheses. So let's start with restrict. It's pretty obvious. All this stuff is pretty obvious, and we've looked at this before. We're in chapter 4, but we're looking at this a little bit more formally, I guess. So we want all the parts where the weight is less than 12.5, and we end up with this. It's a restriction because we only get back a subset of the original rel bar relation. And what happens is the way this works is each tuple is examined and this is evaluated, and if it's true, it's included, and if it's not, it's not. Projection means just selecting some of the columns and not all the columns. This is normally the way you do it for each part. For example, let's say we're only interested in the part number and the color and the city, and we're not interested in the part name or the part weight. This is how we express it. We express it as a set of attributes, a subset of all the attributes, and with this P here. This is another way to express it in his relational algebra language. Unfortunately, there's no way to do this in SQL, which is kind of a bummer when you're dealing with tables that are 150 columns long, which some of my tables, some of the stuff I have had for I created a couple databases back in 2005, and they're still going, but I just kept adding attributes, and they're huge, and sometimes, and there's a lot of crap in there. There's a lot of crap columns in there, and it would be nice if I could just list what columns I want by listing the crap column, by telling which columns I don't want, but can't do that. With this, when you're doing a projection, sometimes if one of the attributes, or if none of the attributes that you're projecting, if there's no set that could be a key, a primary key, doesn't qualify, then you're likely going to end up, or I think maybe you are going to end up with duplicate tuples. You don't in this case because one of the columns you're choosing is the actual key column, so you're going to have, it's going to be unique there. But if we were not let's say we wanted to do a projection on let's say we didn't care about P&O and we only cared about color and city. And so let's say we're just doing this. Well, if we're just doing that and we take out this column, or if I can do that. Anyway, we end up with 2 red Londons. Ooh, 3 red Londons. 3 red Londons. So so then we wouldn't have a relation, because a relation cannot have duplicate tuples. Or if we were dealing just strictly in the world of relational algebra, which we are right now, the resulting rel var would only have 1 red London, and so it would end up with a red London, a green Paris, a blue Oslo, and a blue Paris. But yeah, I'll do that. Let A be a set, then every subset of A is a set. It follows that every subset of a tuple is a tuple. Every subtuple is a tuple. Every subset of a heading is a heading. Every subset of a body is a body. That's nice. So is this what I just said? Boy, I don't believe that I really probably I probably subconsciously remember this set of slides from the last time I spoke of them. But anyway, so this is what I was just saying. If you actually take out, if you weren't interested in P&O, just the color in the city, you would only end up with 4 tuples like this. There's another way that you can express it in his language, and duplicates are eliminated, of course. If we do this SQL, they're not. I don't think. Probably not. Let's see. We have our web servers now, right? Do I have one, right? Yeah, I do. If I can remember. I can remember this. Oh, okay. Can't I save it? No, let me save it. So let's see. Go in here, and this is just. Oh, didn't I put something in here? Oh, I thought I didn't. Did I have another one? I must have.
I remember last time you logged into the wrong one or something.
Oh yeah, I did, didn't I? Oh, I did, didn't I? And that's what I did this time. Logged into the wrong one. Yeah, that's what I did. Log out. You're right. So I want to go to 1. Oop, not there. 1. There we go. There we go. Thank you. Ooh, go here, and there we are. Parts, supply parts. Okay. So we were in here, and we were projecting. So I'm going to edit the line, and I'm going to say, instead of select, let me make this bigger. So instead of selecting that, I'm just going to select color and city. And what do I get? Now watch, you only get 4 records. Let's see. Oh, there we go. See, we got red London, red London, red London. So what we have to do instead is we have to do this. distinct. And we get just the 4. Anyway, that was just a little side note. Closure example. Okay, this is a closure example where we have, okay, normally before we had this, P, and then this is the projection part. And what we're going to do is we're going to replace this rel var with this rel var, you see. So that's a rel var inside of a, you replace a rel var with another expression that produces a rel var. And that's this closure thing. So, it looks like this. First we do the projection, and then we did the, first we did the restriction, then we did the projection. Note use of parentheses, so restriction is done first. In tutorial D syntax, restrict and project, we have a relational expression denoting the relation, and then the word where, and then we have a Boolean expression that can be evaluated for any tuple T of R by examining that particular tuple in isolation. So, we aren't looking at at any of the other tuples. We just go down the line, one tuple at a time, and we evaluate this expression on that using that tuple's data or using that tuple's attributes. And if this expression comes out to be true, it's not, it's included. If it's not, it's not included. Same with the all but here. Okay, so union. The operands have to be the same. The operands must be of the same type. Right. Operands have to be of the same type. What does that mean? It means it has the same heading. So, the operands, this is one operand, and this is another operand. And so, and we're experiencing some closure here. We're witnessing the closure property because this is a tuple and this is a tuple, and so this could be just like some tuple that's got the same header as this other tuple. Anyway, this is an expression that represents a tuple. It's not just a letter. It's just a letter that's got some operator in there. Namely, a projection where we only want to see the city. So this gets cities. This gets cities such that at least one supplier or at least one part is located in that city. So this basically takes the set of cities that comes from the suppliers, all the set of cities that have all the suppliers, and we union it with all the set of cities where there are parts, and then of course you get rid of the duplicates and you end up with this set, I guess. So operands must be of the same type, and the result is the same type also, obviously. Suppose parts have an extra attribute of status of type integer. So let's say that the parts table has an extra attribute called status. Maybe it's a status of the part. A get city status pair is such that at least one supplier or one part has that combination. So that's kind of a dumb example, but I don't know. So we have so we're taking we're taking all the city and status we're taking this. Well, first we're projecting the city status field of the parts, of parts in the city status field of suppliers, and we're just taking the union of the two. And so, you know, the point here is simply, well, we know what union is, but this point also drives home that the order of the attributes don't have to be the same. They probably do in SQL, but intersection. Operands must be of the same type, and in other words, they have the same heading. And so here, for example, we're getting cities where we're taking the intersection, which means the city that the resulting relvar, or resulting relation, only has cities where it's present in both parts table and suppliers table. And from this I gather that in the parts table there are parts in London, and in the supplier table there are suppliers in London, and in the parts table there are parts sitting in Paris, and there is at least one supplier in Paris. So, and also there are no other cities where there is both a supplier and a parts warehouse, I guess. This doesn't tell you if there's more than one, because the duplicates are eliminated. Operands must be of the same type. Okay, here, for example, this is the same example, except for intersection. Sometimes I think that, you watch the videos, you watch his videos and you watch the class, the class he's teaching, and the questions that they ask, and you can't really judge whether they're good programmers or not. We assume they're programmers, right? He's teaching seasoned programmers about databases, seasoned programmers that know nothing about databases. But sometimes those seasoned programmers, I don't know, they don't seem very, either they're not very interested, or sometimes the questions I think they ask are kind of dumb. But that just could be, you notice their age. Their ages, especially that one guy, that one old dude there with the long hair. It could be that his mind is just, he's thinking of he knows programming well, but when it comes to this logic of databases and so on, when we start talking about SQL, and we're really dealing in the tuples world, we're not dealing in the table. It's not two tables and there's an operator in between, and that operator is applied to the two tables and you get a resulting. That's not how we think. We're thinking of, we have a table full of records, and we're going to get rid of some of the records because we don't need a bunch of these records, and oh, by the way, we only need these fields, and so that's more or less how we're thinking. I've heard more about people that are really good in SQL that aren't that good in programming. Now I don't have a lot of experience with, but in my old age, and I've met a lot of programmers, a lot of database people, it seems like programmers aren't that uncomfortable with SQL, but people that are like database folks that got into computers because they like writing SQL and they like doing the database and database administration and stuff, and they can whip out SQL. But as far as writing a big long sequence of instructions that have loops in it and all that, they don't feel quite as comfortable with that. But anyway, that's purely anecdotal. So we have difference here. Difference is kind of sort of like intersection, except for you're not keeping the stuff in the middle that's common. You're getting rid of the stuff in the middle from the first rel bar. And the only reason you use the second rel bar is so you can match up what's common in both. And so as a consequence, this is the only operation that's not commutative, as they say. You know, S minus P. You know, S minus P is different than P minus S. Whereas all the other ones, it doesn't matter if it's S intersect P or P intersect S, or you know, union or any of the other ones. But that's because, you know, subtraction is that way too. Subtraction, multiplication, addition is the same thing. So so here we have, let's say we have a set of cities, from suppliers, and we want to minus the set of cities from parts, and we're going to end up with, there is only one city that is in suppliers that is not in parts, and that would be Athens. Mr. S6, I guess. S6, I guess, is Athens, or S5 or something. And again, you know, operators or operands must be the same type. In other words, headings have to be the same. The order of the attributes doesn't count. So suppose we do have status for parts, and this would be get the city status city pairs such that at least one supplier has that combination that no part does. You know, so that's what we think of, or that's the type of problem that we are attempting to solve, where the solution is to do the minus. This is just another way of expressing. If you're doing more than one of these operations in a row, you can express it this way. Instead of doing Rx operator Ry, you can have the operator and then have an expression list. That's just a way of expressing it. So if you have Rx op Ry op Rz, you can put op and then Rx comma Ry comma Rz. You can do that with union and minus also. We can use rename. You know, okay. So we're starting to get a bunch of things in here where, if we want to, let's say we want to do these kind of fancy functions like union and all that, and intersect and minus, and for whatever reason, and when we made but we weren't anticipating this when we were creating our tables originally, or our rel bars or our relations, and so we didn't name them exactly right, for example. And so fortunately, both SQL and this tutorial D provide this rename function where you can rename anything, rename an attribute something else, and that way its header will match. Also, we may want to rename them so they're different. Like let's say we want to do a natural join of suppliers and supplier parts and parts. Let's say we want to just do a natural join of all those. Well, we would want SNO to match up. We would want the SNOs to match up. We would want the PNOs to match up, but we wouldn't want the cities to match up because they mean different things. The SNO and the PNOs, they mean the same thing, but so we could use rename and change. We can leave supplier city as city, but we can rename parts city as maybe P city, and then we do the join. We do the natural join. The column names, are named properly, so the natural join will work. When we're joining, another way to we may have columns that we want to natural join, but they're not named the same. Like, what if part numbers in the parts table were named, PNUM, whereas in the supplier parts table, it's named PNO, for example, more likely something like, it's called SNO in supplier table, and it's called PNO in a parts table, but in the supplier parts table, it's called PNUM and SNUM, let's say. But you want to do a natural join thing. Well, we don't use rename there, but when we're doing the join, there's another thing we could add on to join called on, and on simply is an expression which matches up the two columns. So we would say on, and we'd say PNO equals PNUM, and SNO equals SNUM. That's more common, because for all of the column names to magically be named correctly for these natural joins, just because you want to do natural joins is not really that practical, except for when we're doing these academic exercises. But anyway, because of closure, we can do all this stuff and nest it all up, and we can end up, coming up with the result that we want to, regardless of things like what the names, what we chose to name them when we were creating the table and so on. So we have this rename. Well, this is kind of the example I was saying, where we might want to change the name of it so we can, use it in one of these operations. So here's some exercises. What is the formal reason for prohibiting duplicate tuples in a relation? We have a formal reason, but can you think of a pragmatic reason? Yeah, you can read what he says about that. What do these expressions denote? You can look and you can figure that out. Anyway, so let's go see what the quiz looks like today. Let's see what else is in La Lima. I haven't finished going through this yet. Assignments. We don't really have any assignments yet, do we? Quiz 5. This is today's quiz, right? All right, so what is this quiz? I didn't look at this yet today. Put this up a while ago. Let me look at this. This one here. All right, we're going to, this is on projection, restriction projection, and the importance of closure. Okay, imagine a relation. This is pretty dumb. This is all easy stuff. Imagine a relation E. So we have these employee database, and we have these numbers, employee numbers, and we have these fictitious characters here, and we have this guy's null is H26, and this is H32, and H28, and CC1. I don't know where these came from, but and this other information. Okay, write a tutorial D formulation that produces the relation shown to the Write down here. You're supposed to write the tutorial D formulation that will produce this from this. Okay, you do something, and it produces this. Okay, so it's going to say E something, and that's all it is. E something. Start with E. All right, next one. The tutorial D formulation projecting the city and zip codes is this. That's not this, is it? Oh, no, never mind. There's a restriction in here. There's a restriction and a projection. To do this, you got a restriction and a projection. This just produces all the zip code city zips, and so that would be Honolulu 96828, IA 96821, Honolulu this one. You wouldn't have this one in there, but you'd have this one in there. And so you're supposed to write the formulation. no, the formulation there is, oh, I just told you what it was. Well, maybe you weren't paying attention at home. All right, third one. Oh, well, anyway, the third one is you can figure that out either. I don't want to even say it because it's obvious what I'm getting at there. So, all right, this looks like a pretty easy quiz. If you're not done with your quiz, you can. This class goes till 2. Okay, it's not that early. So, you can finish your quiz. But I don't have anything more, pretty much. Do you have any questions? We've gone a long way to covering Chapter 4. This will get more interesting after a while. You're learning some good theory here. So thanks. Thank you. Yep. See you. Thanks for watching.